Okay, here we go again. So number 17 asks, how many valence electrons do the following elements have? Now, we've talked about how the main group elements exist on either side of the periodic table, and it's very reliable in terms of how many valence electrons those have. For a variety of reasons having to do with d electrons, this area is a little more iffy. So when we talk about valence electrons, we've always involved these atoms, and we haven't talked so much about the bonding that happens here in the center. So counting number of valence electrons is just as simple as knowing what main group the element exists in. So you have group 1 and 2 on this side, and then you just skip over here and you pick it back up and say 3, 4, 5, 6, 7, 8. And then it's really just that simple. The valence electrons are going to be equal to whatever the main group number it's in. Also, if you didn't know this, you can see how 3 and 13, 4 and 14, 5 and 15, 6, etc., how these connect. It's essentially just the actual group number minus 10. That's the number of valence electrons for these. If your periodic table isn't labeled with the main group elements and you don't feel like labeling it up here. Main group elements typically, just as a side note, get this little A after them. So if you look up at my periodic table on the classroom wall during the test, you'll see an A next to it. Okay, so at this point it's pretty straightforward. Astatine is in group 5, so it has 5. Potassium is in group 1, so it has 1. Fluorine is in group 7, so it has 7. Boron is in group 3, so it has 3. Silicon is in group 4, so it has 4. Calcium is in group 2, so it has 2. And then selenium over here, 6. And neon, 10. If you're looking for an element on the periodic table and you can't find it and you're starting to get frustrated, just go to the next one and then come back to it like a minute later. That's a little tip I found when I was in high school and college and I would look for something and couldn't find it. That's what I do. Usually the second time I went back and looked, it got more easy because I wasn't getting all frustrated because I couldn't find a stupid letter on the periodic table. Okay, so the next question says, why do elements in the same group tend to have the same property? And it really just goes back to the question we just answered, because elements in the same group, remember, groups are up and down, elements in the same group tend to have the same properties because they have the same number of valence electrons. So like, for example, all of the noble gases all have stable octets. They have 8 valence electrons, except for helium, it has 2. Everything else has 8, so these are all very stable, they're all very non-reactive, and they're all also gases for that reason. So same group have the same properties. It's because they have the same number of valence, not just any electrons, but valence electrons. Okay. By the way, to get all the bonus points on the test, these answers that you write in on your study guide need to be in your own words. If I see that you've copied what I have in this answer key word for word, then that tells me that you didn't really do this or try this on your own, that you just kind of watched the video and filled things in as you go along. And that's not going to help you prepare, so I can't give you bonus points for that. 19, the better thing to do is to try to answer these yourself and then go back and check your answers. All right, 19 says list 2 elements that would have the same properties as these elements. So rubidium is in group 1. So I could say that potassium and cesium would also have the similar properties. Or lithium or sodium would also work. Magnesium, I'm going to say beryllium and calcium because they're also in the same group and they're just directly above and below. And then finally, krypton which argon and xenon. So if Krypton repels Superman, then probably argon and xenon would too. Although that's all fictional. Okay, number 20. Define the following terms and draw a model that represents each. First one, chemical bond. So a chemical bond is a, it can be a transfer or sharing of valence electrons between atoms, okay? And I'm going to put S and then parentheses. Well, it's always going to be more than one atom, right? So an example might be, we've talked about salt quite a bit in ACl. So Na has a 1 valence electron because it's in group 1, and chlorine has 7 valence electrons. So sodium is going to donate its electron, and chlorine is very electronegative, so it's going to take that electron, and then you'll end up with this Lewis structure where the electrons have been transferred in this case. Okay. Oh, hang on just a second. Oh, okay, thanks. Appreciate it. Next definition, ionic bond. That's in an ionic bond. Remember, this is only going to happen between a metal plus a nonmetal, right? Because there is a huge difference in electronegativity, right? So essentially, we just talked about electronegativity trends. So these atoms are very electronegative. They're very electron hungry. These are not electronegative, and they have a very low ionization energy. So they will give up electrons easily. So what happens in ionic bonding? It always goes like this. The low ionization energy atoms, the metals, give up an electron, and it is not shared, but it's transferred to an atom that is more electronegative over on this side of the periodic table. So it is a transfer of electrons. Metal plus nonmetal bond, transfer of electrons from metal to nonmetal. Okay, and then this would be the example, sodium and chloride. Okay, I didn't give myself a lot of room for the next definition, but let's just make it happen. Covalent bond. This is going to be a nonmetal plus a nonmetal. Okay. So why a nonmetal plus a nonmetal? Well, nonmetal and nonmetal, like let's say carbon and nitrogen, there's not a big difference in electronegativity. They're both super electron hungry. So instead of one taking electrons from the other, they're going to share them. Although the more electronegative element will hang on to them a little bit more. We'll do a little more sharing. So this would be a polar bond between carbon and nitrogen. But we'll talk about that in a bit. Nonmetal plus nonmetal means a bond with sharing of electrons. An example would be like carbon and hydrogen. Okay. And I'm just drawing it because it's super easy to draw the Lewis structure. They're all sharing. Hydrogen is in group 1. Remember, it's our only nonmetal that's over here. And it has 1 valence electron. Carbon has 4. So those 4 valence electrons in carbon are shared with a hydrogen. And you end up with the chemical CH4, and that's totally balanced. Okay, so last but not least is metallic bond. Metallic bond is between metals and more metals bond where electrons are delocalized. Okay? If you are delocalized from your house, then that means that you can travel around. You can go hang out at your friend's house. You can go to the store and get, I don't know, a snack or something. You can move around, right? Well, it's the same thing with metallic bonds, okay? So let's say silver, for example. Silver is a great, excellent conductor of electricity. So these are my silver nuclei. And then the electron can just go anywhere. Okay, it can be here, 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 here. It can travel wherever it wants to, okay? So you could represent silver like this. In our reading, they represented it where it looked like a bunch of yarn around. So that's going to be my representation of silver. I know it's not very pretty, but at least it gets the correct idea across. Okay? Why do atoms bond? What is the goal? This goes back to the octet rule. Okay? Atoms are either going to gain to get to 2 valence electrons or 8 valence electrons. To form a stable outer shell, okay, that's either 2 or 8. 2 or 8 electrons in the outer shell, okay? Number 22 says at least 2 properties of ionic compounds, 2 properties of covalent compounds, and 2 properties of metallic bonds. So ionic compounds, covalent, metallic. One thing we learned about ionic compounds, so salt is an ionic compound. We know when we dissolved it in water, it conducted electricity. So conducts electricity when dissolved. We also know that it can break easily, so it's brittle. We also know it has a high melting point, although not as high as a metal. So metallic bonds, there's a bunch of stuff we could say about metallic bonds. They don't dissolve. Or metallic, compounds, I guess I should say. They do conduct, they're excellent conductors of electricity because, again, their electrons are delocalized. They have the highest of all of the melting points because it takes a lot of energy. It is a very strong bond. So there's some properties there. Now, covalent bonds, compounds, they do not conduct electricity. They have the lowest melting point. They don't even conduct electricity when they're dissolved. They tend to be organic substances, meaning they tend to be the compounds of life. Okay. Okay, so number 23, classify the following types of bonds as metallic, ionic, covalent, or polar. Metallic, ionic, covalent, or polar or nonpolar. So, what color haven't I used? Let's use black. Na and Cl. Well, Na is a metal, Cl is a nonmetal, so that is going to be ionic. Okay? Bromine and bromine. Bromine connected to bromine, they're both obviously nonmetals, so this would be covalent. But would it be polar? It would not be polar because they both have the same electronegativity value. Hey, guys. So it's nonpolar covalent. Zinc and oxide. Zinc is a metal over here, and oxide is a nonmetal, so that's going to be ionic. Silver and gold. If you had a silver and gold alloy, that would be two metals mixed together, so that would be metal. All right, we'll pick it up later.